Hey, this is Dr. Hines. Welcome to our our second virtual chem lab here at LSMSA. So we've got some equipment set up over here. We're basically going to find the density of some liquids, find the density of some solids. And so I'm just going to kind of introduce a little bit about density. I know you've talked about this in class already, but we're just going to review it a little bit, talk about some of the measurements, and talk about percent error calculations. So a little bit about density itself. In class, you've talked about mass. Mass is the amount of matter that you have. The amount of space that it occupies is the volume. And it kind of makes sense that if I have a large volume of something, it's probably going to be a lot of mass, and vice versa. If I have a lot of mass, it's probably going to occupy a large amount of volume, perhaps. But what really wasn't quite understood was the fact that the ratio of mass to volume, if you have a pure substance, this ratio of mass to volume is actually a constant, assuming that temperature doesn't change or pressure doesn't change as well. So this ratio of mass to volume, it's a constant, and we define that as density. All right, so what we're going to do in today's lab is we need to somehow determine the mass of our substance, which you've already seen how to use an electronic balance, so we know how to do that. And then we need to determine the volume of the substance that we have. And we have both a liquid and a solid, so the techniques of how you find the volumes of the liquid and the solid are a little bit different from each other. How do you find the mass of something? You kind of pretty much just weigh it on the electronic balance. Now, it might be that you have to weigh something empty and then put something in it and then weigh it again and subtract the two. We may have to do that, or just simply maybe just weigh the object. When you find the volume of something, it kind of depends. I mean, how do you find the volume of a liquid? Let's put the liquid in some particular type of glassware, which might have been on your laboratory equipment quiz, a piece of glassware that holds a very specific amount of volume in it. That would be very helpful for finding the volume of a liquid. To find the volume of a solid, how do we find the volume of a solid? If it's a sphere, if it's a cylinder, if it's some sort of a cube-like structure, you could maybe measure it with a ruler in some sort of fashion. But the technique that we're going to use to find the volume is to use water displacement. So imagine having a container of water and you read the level of water in it, and then you put something in it, you would expect the water level to rise. And if we look at how much the water level rises, that displacement is going to reflect the volume of the solid that we put in there, okay? So that's kind of the background of what we're doing in terms of like what density is and how we're going to kind of measure it. And when we go over to the lab over here, you'll see the finer points of the technique. Now, the last thing I need to talk about is, this is a common calculation for most labs, calculating your percent error. Now, for a lot of the things that we're going to do in lab, we kind of know what the answer should be. So we have like an expected answer. Maybe you might want to call it the accepted answer. All right. Some of the things that we're measuring the density of, we know what the density of that material is supposed to be. So there's an expectation or an accepted value for it. And then you actually do the experiment and you get the actual density or the measured density, perhaps, whatever terminology that you want to use. And it wouldn't be uncommon for what you get in the lab to not be what you were expecting to get. So we can calculate a percent error from this. And here's how you would go about calculating the percent error in your experiment. So the percentage is going to be equal to, I mean, this is the way that I do it. I take the actual result, the one that you got in lab, and I subtract, let's say I subtract the accepted value. All right? Now this actual value, it could actually end up being smaller than what you were supposed to get. So I could say just take the positive result of that, or maybe getting a little bit mathy for you here, let's just take the absolute value. When all is said and done, just get the positive result of this subtraction. So what we want to do is we want to take a look at the difference between what you got versus what you were supposed to get, and then compare that to the accepted value. So this is gonna, I mean, it's a ratio, that's what percentages are all about. And so the last thing that we need to do is just multiply this by 100, and this would give you the percent error for this. And an example of what this could look like, let's suppose you did this experiment. We're gonna be doing aluminum. Let's suppose in your experiment, you got your aluminum value to be, say, 2.68. That's the value that you got in the experiment. Now, I know for a fact that aluminum is supposed to be 2.70, okay? So again, this is what you got in the lab. This is what we were expecting to get. And you're a little bit below the expected value. So I'm gonna just take the absolute value of that so it becomes a positive result. And then down in the denominator, we're supposed to divide by our accepted value. And what I do not have with me right quick, although I see one over there, could you grab me that calculator right quick? So we're gonna plug these numbers in, and we're just gonna see what kind of error that we get, okay? And again, I'm always gonna want the positive result on top. So 2.68 minus 2.70. I have a result, change it to positive, divide it by 2.70 times 100, and I get a percent error of, and we should have been doing significant digits by this point, I think. So if we do the significant digits, I know I'm going to get 2 significant digits in the numerator, and that overall is going to give me 2 significant digits in my calculated result. So I'm going to call this 0.74% error. Now, generally, I mean, is this good? Is this bad? I mean, this is like really good. This is really good. Typically, if you want to publish your results in a peer-reviewed journal, I'm going to say that your error needs to be less than 5% error to be like acceptable, unless perhaps the measurements are known to have larger percent errors. But this is pretty good. This is very achievable in this lab. If you get something like 5% or 10%, you're really not recording some sort of mass or volume correctly in your experiment, okay? So hopefully this kind of helps you out with how the experiment's done, and probably more importantly, looking at how good of a result that you got. Okay, we're gonna move on to the experimental part.